Hello everyone, I am Dr. Pallavi Ram. Welcome to my channel Probabilistic Revelations for Engineering. In the previous videos, we have discussed about a probability space. It consists of the sample space, then the event space, and the probability measure. The probability measure satisfies these three axioms of probability. In this video, we are going to discuss another probability. This is called as conditional probability. Conditional probability is written as probability of an event A given an event M has already happened. So probability of A given M. It stands for probability of an event A given that M has already happened. And by definition, we can write this as probability of A intersection M divided by probability of M. So this is the definition of conditional probability. This will help us in calculation of many different events, which we will see later. So first we will prove that this is really a probability measure. So to prove that it's a valid probability measure, this probability should satisfy all these three axioms. So let us verify whether it satisfies the three axioms or not. So first let us find out what is the probability of the sample space omega given M. So this should be equal to probability of omega intersection M by probability of M. But omega intersection M, omega stands for the complete sample space. So intersection of sample space with M gives us only M, because sample space comprises of all the possible outcomes and M is an event which comprises of only few of the outcomes of omega. So this will be probability of M divided by probability of M. So the answer is 1. So this verifies the first axiom of probability. And in the second axiom, we can observe that in any probability of A given M, probability of A intersection M and probability of M, the numerator is greater than or equal to 0 and even the denominator is greater than or equal to 0. So hence the answer, overall answer is also greater than or equal to 0. So thus it satisfies the second axiom of probability. Now coming to the third axiom, let us assume that two events A comma B and also M, they all belong to our event space F. And A intersection B is a null set. Now if we try to find what is the probability of A union B given M, so by the definition of that conditional probability, we will expand this. So this becomes probability of A union B intersection M divided by probability of M. So we see that union and intersection, that the distributive nature is there here. So A union B intersection M can be written as probability of A intersection M union B intersection M divided by probability of M. So now let us see what is the nature or what is the relationship between these two events, A intersection M and B intersection M. So we know that A intersection B is a null set. So A intersection M and B intersection M, since A and B have no common elements, this A intersection M will not have any elements that are present in B. Same way, B intersection M will not have any elements that are in A. So thus we can say that this intersection, this is also a null set. They will not have any common elements. So we will call this as C and we will call this as D. So it appears as if C intersection D is phi. And here in the numerator, it is C union D. So to write probability of C union D, where C intersection D is a null set, we have to invoke our third axiom of probability. So our third axiom says A intersection B phi means probability of A union B is equal to probability of A plus probability of B. So invoking this axiom for C and D, we can write this is equal to probability of A intersection M plus probability of B intersection M and divided by probability of M. So the first one, by definition of conditional probability, we can write it as probability of A given M, and the second one we can write as probability of B given M. So we started with probability of A union B given M, and the answer is probability of A given M plus probability of B given M. So the meaning is the third axiom of probability is also being satisfied by conditional probability. So thus conditional probability satisfies all the three axioms of probability. Hence, conditional probability is a valid probability measure. So this is a valid probability measure, since it satisfies all the three axioms of probability. Now let us see one example on this. So let us think of a dice experiment. So let's say rolling of a dice is our experiment. And when the dice is rolled, we know that, let us say, we know that an odd number has appeared. So we say that an odd number has appeared or occurred. Now we want to find out the probability of the event called 3, 5. So what is the probability of occurrence of 3 or 5? So this probability, this event's probability, we want to find. So a rolling of a dice is our experiment, and we know that some information is given. We know that an odd number has already occurred. So let us name them. So let us say M is an event which has already occurred. So that event is 1, 3, 5. So this event has happened already. So we need the probability of another event called A, which is 3, 5. So given that event M has already happened, what is the probability of A? So this is what we are supposed to find now. So what we'll do is we'll solve this problem in two ways. One, by using the conditional probability definition that we just discussed, and the other one without that. And we'll tally whether both the answers are same or not. Now, if we don't use the conditional probability definition, we know that our outcomes are only 1, 3 and 5. Why? Because this event has already happened. So that implies that our outcome space now is only 1, 3 and 5. Why? Because we know that this event has happened. So there is no chance that 2, 4 and 6 has appeared because we know that 1, 3, 5 odd number has occurred. So now, because these are three different elementary events, so probability of each one of this elementary event or each one of these outcomes should have been 1/3. Hence, the probability of A, which means the probability of 3, 5, since 3 and 5 is a group of two different elementary events, we should say that this probability is 2/3. So this is without using the conditional probability definition. So this answer, whatever we wrote, it is not just probability of A, it is probability of A given this condition. The condition is odd number has occurred. So given this condition, this is the answer. Now let us invoke the definition of conditional probability and resolve this problem. So we need to find probability of A given that M has happened. So that is probability of A intersection M by probability of M. So when we do probability of A intersection M, this becomes probability of 3, 5. And this will be probability of 1, 3 and 5. So in the experiment of rolling a dice, totally 6 outcomes will be there. So 6 elementary events are possible. So since the numerator comprises of a set 3, 5, which is a group of 2 elementary events, its probability will be 2/6. And since the denominator has 3 elementary events, its probability will be 3/6. So hence the probability will be 2/3. So thus the conditional probability definition, if we apply, the probability answer is 2/3. And even without applying that definition, by considering our new outcome space, we also calculated the probability of A given M as 2/3. So thus conditional probability, when we apply the definition, we don't need to define our new outcome space. So with the help of directly this definition, we can calculate the answers. More examples on this we will see in my later videos. Thank you very much. If you like this video, please click on the like button, and if you haven't subscribed to my channel, please subscribe. Thank you very much.